I think the video just started. Sorry about that. I'm going to wait for a couple minutes. We have a lot of attendees that are still clicking on, so I will just give it just a minute before we get started. Okay, well, I don't want to keep you guys waiting, so we're going to go ahead and get started. I'm Christy Vomano. I'm the Director of Engineering for Electrical System Studies and Power Generation and Energy, coming to you from my beautiful basement. So we are going to talk to you today about solar integration, and I have a couple of excellent colleagues on that will be talking to you. But before we get started, I want to give you just some general information and housekeeping type stuff. So there will be PDHs, a 1 hour PDH that will be earned for this webinar, and you will get, you can use a link that will come at the end, an email for that. We also will be having you enter questions in the chat box, and I will track those as we go through the webinar, and I will bring those to Steve and Mike Bloater's attention as we go. And also we will have interactive polls going on throughout the webinar. So please participate in those polls as much as possible. And I guess the last housekeeping item to remind you of is that we will have a handout for all of the presentations that will be available at the end. So now I'm going to want to go into give you an introduction to our two presenters. So we have Mike Bloater. He's the Associate Director for our Substation Protection Controls Group with over 30 years experience in electric power. Mike also is the IEEE Power System Relay and Control Committee and also System Protection Subcommittee member. The other colleague that I have joining you is Steve Miller. He is a consulting engineer for us with his expertise in electrical system studies. Steve has over 40 years of experience in electrical power, an IEEE member of several committees, including Power System Analysis, Computing and Economics Committee. Also, he's part of CAM's Task Force on Understanding Prediction, Mitigation, Restoration of Cascading Failures, as well as AMPS and several other committees. That is a very extensive list we did not want to include here. So with that, I'm going to turn the presentation over to Steve Miller, and he will get us started. Thank you, Steve.
Good morning or good afternoon, depending on what time zone you might happen to be in. We are going to make our presentation on solar integration. The first step in integration, of course, is interconnection. And you'll see as we go through the presentation that theme then plays out throughout the process. So one of the things that we like to talk about is that, you know, the interconnection basics have been around for some time. Basically, they start with the interconnection applications, which means, oh, okay, I've got something I want to have grid connected. You know, who do I contact and where do I do it? So you have to file an application. Like I said, this is basics. And then there are, and they go by different names, or rather, I should say the names have been permuted a little bit, and we'll talk about that in a second. But basically, the process is a feasibility study, system impact study, and a facility study. I expect many of you are familiar with that. And then the picture on the right is mostly a decoration. But what it implies is some of the details that are important for solar interconnections in particular, and in more general inverter-based resources in general. So, and that's the general class of things that we're talking about. So one of the things, again, is the basics are frequently the same. So let's move on here. We have some questions that we'd like you to answer here right off. Maybe if we can get those answers, we can provide some feedback or orient the presentation a little bit better as to what your interest might be. So we've talked about, do you work for a transmission owner or operator? That's a grid owning company, American Electric Power, ITC, PG&E, all would be examples of those, of course. I work for an independent system operator or a RTO. Those are, of course, the organizations that operate the grid, CAISO, ERCOT, ISO New England. So if you work for any of those, I am a solar project developer. I work for a solar project developer. Just says that you're at some phase interested in developing a solar project and are doing that kind of work. You're a contractor. Frequently you interact directly with developers, but as a contractor, you're going to execute all or part of a solar project. And then last but not least, we have the category of consultants. If you're something else, don't hesitate to put it in the chat. I'm going to move on here.
Steve, we have our results for the quiz, the poll. It's a 41% consultant, 33% transmission owner, operator employed by them. 13% I work for a solar developer, and then 13% I work for a solar project contractor, and 0% I work for an ISO or RTO.
That's good. So, when I'm throwing shade, it will be all at ISOs and RTOs today. So not that I'm going to throw much shade. Anyway, the origin of the process, and this is very, very important, is where did it come from? Because the point I'm going to make here is that the basics haven't changed much. So in 1992, the nation, Congress passed the Energy Policy Act of 1992. That act has been updated 2 or 3 times since, but the basic bones, the basic idea of open access was established in that. And then, as the politicians normally do, they go off and they take 10 words in the law and turn them into 1,000 words into the regulations. So part of those regulations was to come up with some pro forma tariffs, which included how you integrate generation into the process. The bones of that remain the same. Okay, so all of the ideas from the mid-90s really still exist in some form in all of the stuff that we do today. So that's, things change slowly. Now, I will say that there are some current efforts. There's a lot of frustration with the interconnection process. If you're a solar interconnector, you know that it can be very frustrating. If you're a transmission provider, all of the work that needs to be done is maybe frustrating. So there are some efforts to change those processes. Bet you're all wondering why I put that picture on the screen, so and this is all stuff that you may know, but humans have a tail. They actually have a tail that up until a few months, they have a number of vertebrae that you lose. So a vestigial tail describes a remnant of a structure found in embryonic life. So my point here is that the DNA can stay for a long, long time. So we'll now go back to the more serious sorts of things that we're talking about. And now we're going to be getting into stuff that is maybe not sort of rote for many of you on the line, but is more of more of the details that you need to know. And maybe this is just a reminder. First, in the interconnection process, there's virtually always a public queue. I'll talk about the exceptions to that in a second, but you can find out who's in the queue. You know, sometimes there's almost always there's an attempt to hide the actual developer, but the list is there and the spot where their interconnection, the size of it, the fuel, in this case solar, is always there. The standard processes now are something called a cluster study, right? That wasn't the way it was in the beginning, but cluster studies were always available as an option right from the pro forma invoice. And the cluster studies usually imply a fixed window. All right, this group of, we're open for this time, and so whoever signs up, you will be included in that study, you know, by a date certain. So for example, the date in MISO for the next cluster is September 15th. The second tenet of a cluster study is that the costs of the network upgrades will be allocated among the participants in the study. And there's where a place where the details get interesting, because the details aren't consistent. How that allocation process works is not uniform. And then usually they start out with a initial steady state study, power flow or short circuit, with a subsequent round of dynamics. All of those three may be done in one process, but the modern step is not to. So up above, I talked about public queue. The real exceptions, particularly among the ISOs, is ERCOT, which doesn't publish a queue until after the studies are complete, and New York ISO, which lets developers participate in the study process in a much more significant way than anywhere else. A key thing is reactive power. You know, we'll ask some questions about reactive capability later on, but reactive capability and interconnection requirements for PV and wind plants. I have a reference there to a group that does technical work. And then the key thing, an area where we're big on right now, is emerging special studies. So because of the difficulty in studying solar integration, BESS integration, wind integration with the standard power flow and short circuit and dynamic tools, many folks are going to electromagnetic transient type tools. In the largest case, that's PSCAD, and they're insisting on PSCAD studies. It's currently fairly uneven as to how they might do that. So I was talking with my colleague Mike here, and you know, ISO New England is going to, we need all generic models, especially for stability studies, wishing for the same thing for PSCAD, where other places are saying, no, we absolutely need to have a user-defined model. So there's a lot of details in there, and so that's an area of study, and that's an area of study that has held up the integration of renewables in many cases. So years ago, this was years ago, back in the 2000s, and I was never involved as a participant or in a money sort of way, a contractual sort of way with this project. But for a variety of reasons, I traced the project, and it was, I think, a good project. Was eventually killed by paralysis by analysis. So there were all sorts of questions that were, it was just studied to death. So that can happen. I don't really expect, you know, this is the type of slide that people tell you not to display, and I don't really expect anybody to, you know, read it and take notes. Our slide presentation is available afterwards, so you'll get this in that. But the main point to take away from this slide is that the ISO interconnection process is open, and we've tried to give you, at least in the ISOs, where you can go to pick up all of these pieces of information. And so that's there. The same is true. There's another way to pick up information where an ISO doesn't hold sway, or where there may be some ISO presentation persistence, like in California, you've got the energy imbalance market. But unless you're in California, the interconnection process is still managed by the transmission owner. So here's a slide that I think may be of more interest to the folks who are trying to move this process along. For people who are requesting studies, these are things that they can ask of the transmission provider or the RTO, and maybe provide a useful way of moving along. For a transmission owner, where there's a certain amount of frustration, you may be able to point the developer to these kinds of options and move things around. So there is a thing that is, and again, all of this traces back to the beginning. It's called an optional study. So if you have something special that's sort of giving people heartburn about your project, maybe the way it's intended to be used. So for example, you may have a question about, how a solar unit can participate in frequency regulation, and you may want a special study to, get on the same page as with that. So optional studies are all possible and available. There is another key idea here. The bureaucrats actually know that they are slow and incapable sometimes of responding in real time. So there's this thing called an engineering and procurement agreement. Now, this is an agreement that in a non-regulated industry would virtually never exist, because it says that if you're a developer or a project proponent, you can ask the transmission owner for one of these engineering and procurement agreements, and at your risk. Okay, so if the project ultimately fails, all the money you spend on this will be gone. You can ask, though, and with a defined scope, to ask the transmission owner to do some studies that would help you move along in your interconnection process. So you might help with, you might fund their procurement of certain materials. You might come up with an engineering and procurement agreement that has to do with checking with availability of land, any sorts of things. I think you're not limited to those except by your imagination. So there are also, and this is where reading the tariffs and digging in, there are special processes called out. So we talked earlier about the idea that everybody was going into cluster studies and that sort of thing. Well, the predecessor was individual studies, and the reason individual studies fell out of favor was there were so many of them, and they interact with each other, that the idea was that you go to cluster studies to solve the problem. But the option to go to individual studies still exists in a lot of tariffs and underlying. So for example, in California, you can get to an individual study as long as you can meet certain technical requirements. And those technical requirements are that the outage distribution factor and the power distribution factors fall below a certain threshold. In other places, you can go to a provisional interconnect agreement. Again, it's a type of agreement that, absent a regulatory sort of arrangement, nobody would ever sign. But it basically says, if you want to proceed with your project, there's some limited studies, and we'll give you a provisional interconnect. If it all blows up, that's all at your risk, but you're able to move forward with that. The next three bullets are maybe a little bit more extreme things that you might leverage. So, you know, and it always at least amuses me, and maybe I'm weird sense of humor or easily amused, I don't know. But when you finally get your generator interconnection agreement, right in the very first sentence or so, it says this does not provide for transmission service. Literally, all you're getting with that interconnection agreement is the ability to interconnect to the system. But there's another thing that's called transmission service, which typically projects get after they are commissioned, and they can buy in a reasonable way or through the open access process. But you can ask for transmission service ahead of time. You'll find that queue is virtually empty. So that's a process that you might use. All of the tariffs have some sort of dispute resolution process in it. You may want to execute that or ask for it. And I think that's actually a mutually beneficial process, right? So particularly if you're a transmission provider, for instance, and you're having trouble getting a firm answer to a question, you know, maybe entering that dispute resolution process in an amicable way really allows to highlight the issue and get it resolved. Finally, there is a fact that I think that many people have discovered. We were a part of a process once where it was used actually, but once you get your transmission, your agreement, your generator interconnect agreement, or even a study agreement back, you have the option to say, hey, we want this to be filed at FERC unsigned. And if there is a process there that there's some contention on, then the advantage of doing this is the burden of proof is then on the offerer of the agreement, the transmission owner or the RTO, to show why the interconnection agreement, you know, shouldn't be signed, or why a cost is included, or what have you. So there are some leverages and some special things that you can do in the interconnection process. Next, we're going to move on to standards and orders, right? So this whole process has all been codified in standards and orders by FERC. So I started this presentation out by talking about, you know, the Energy Policy Act of 1992 and those particular standards. And after that, there's been a huge interest in producing standards and moving forward with that sort of thing. So again, we'll highlight FERC briefly here. Those original orders, which really sort of took things out or started things out, were Order 888 and 890. Now, I have to tell you here, I had intended to do some research to back up my memory here a little bit, but I believe 888 has the original pro forma tariffs, or at least references to them. Then, of course, there's a lot of more modern FERC orders that impact this area. I've highlighted two of them, 827, which is about reactive power, and 842, which is about frequency response from your projects. And these are requirements. They do two things, basically. They say, look, you know, if you're going to interconnect a solar project, you have some minimum requirements to make. But they're also your friend in another way, if you're looking at it that way, is that they also limit what you have to do. They define what those capabilities are. And how do you decide whether you meet that? Well, of course, in general, somebody needs a study. So those are the major FERC things. Then, of course, there's NERC, right? And NERC is really, really, really prolific at creating standards in our industry, right? And for a solar generator, there's a few of them that I've listed here that are particularly interesting. It's important to remember that NERC is actually a creature of FERC. They are a the ERO, Electric Reliability Organization. So NERC actually existed long before the FERC orders and that sort of thing. NERC dates back to a New York blackout in the 60s, right? And the industry was afraid that was going to cause a lot of regulation, so they formed the reliability quotient, electric reliability quotient, and said, hey, look, we're taking care of the problems. So NERC existed 30 years before open access, and they got themselves designated as the ERO. It's important to remember this when you're talking about all the FERC regulations and rules, is where the actual authority comes from. So on my list, I've listed FACT 001. That is a standard that every transmission owner must have that describes their interconnection processes. And it's an interesting one to look at because it may not always be entirely consistent with, you know, the practices that are going on. So if you really want to be expert, you know, you go into that and interpret it and read it. FACT 008, you know, as a generator operator, you have to file your circuit ratings. Those start to become a part of data that is created initially in the design phase. Then there are a number of generator owner operator requirements. I've listed mod 26, mod 27, mod 32, and some protection standards, 19, 24, and 25. We'll talk about particularly 24 a little bit down the road. But these are standards that where the application of them is unclear, at least, or I should say evolving for solar operators. For example, 26 and 27, if you read them, you say, oh, okay, how do I apply this to a solar installation? It's sitting here talking about synchronous generators and a lot of that. But those standards do apply. There are efforts to modify them to account for solar in general, or in particular, and IBRs in general. There's a link there in my presentation. There's a spot where you can get all the reliability standards, their current status, that sort of thing. When you're talking about standards, it's always a good idea to go check that, because it may have changed. No matter how hard you try to keep up, there's no substitute for checking it. And then my final point is to know whether or not the standards apply to you as a generator. You look in the standard, and there's always, NERC has a very fixed way of looking at standards. There's a section in each of the standards as applicability, and if you see generator owner in there, you know you have to deal with that particular standard, or you have to find somebody who can help you deal with it. Of course, we have the old IEEE here, and my colleague, Mike, an old Navy guy, added this little picture. IEEE needed to get moving in the same direction, right? Because we had all of this mandated legislation and what NERC was doing, and IEEE said, ooh, maybe we need to keep up with this, or we're going to become irrelevant. They've done a very good job in keeping up, or a reasonable job, I should say, perhaps, and created standards that people reference and use. Given two examples of those standards. 1547 is the standard for interconnection interoperability of distributed energy resources with associated electric power system interfaces. That's a lot, and you'll see that there are a lot of substandards associated with it. There are different applications of it. In general, it's distribution level standard. There are some holes in it. So IEEE is currently working on P2800, which is interconnection of inverter-based resources. So that's in balloting and will be out certainly. shortly, and it's going to be something that it'll be interesting to see what its impact is. Mike, you were going to talk about these slides. I've been hammering on here.
Sure. So thanks, Steve. So the the IEEE 1547 standard, we have the ride-through capability curves that it's, you know, the 1547 standard provides specifications. And that's one of the key points of the standard, is that it does provide, you know, specifics on how the inverter-based resources need to, or any you know, generating resource needs to operate. But in particular, we have a continuous operation region that within, you know, plus or minus 10% voltage. So that's an important region, that if there's any system disturbance in the area, that we want to make sure that our inverter stays online and doesn't hiccup and drop off. So, and there we'll show some examples later on, but you know, along with that, then we have areas of, you know, shall trip. I mean, we get into areas where there could be a danger or a risk to the equipment. So we want to make sure that, you know, we get that equipment offline to you know, not jeopardize its you know, the health of it. So these are very important. And one thing to point out here is that, okay, you look at the difference between shall trip and continuous operation. Well, okay, if the equipment, you know, is rated to handle you know, the condition, then you don't have to be right on the line. You know, you can be in an area that provides better ride-through capability. So you know, sometimes it's interpreted as, okay, I need to be exactly on these lines, and they're, you know, you have to, you know, base that decision on, you know, setting your levels on you know, equipment ratings.
Yeah, so Mike, wouldn't you say that this is an area of continuing evolution? So this PRC 24 graph is what, at least the second, third, or fourth iteration of graphs in that standard.
Correct, and it's an ongoing effort. So they'll expect changes in the future. So let's move to the next. So we have, this is for
Sorry about that. I probably should have clicked you forward.
No, that's fine. This is for this particular one. We're showing abnormal voltages and voltage ride through. Next one is for frequency.
Same sort of ideas. So I would say too, with the frequency, it's more in its infancy than the voltage ride through, particularly where you have a solar project that needs to integrate with other resources that may be a part of the plant. So if you have a BESS, or maybe there's some wind there or something like that, this is an area, and Mike will go through some stuff later in our presentation about, you know, how this is, what the impacts of this have been in the real world. I guess I'm ready to move on here, and what we want to talk about here is an area that is very, very important, because all that I have said applies, the principle kind of drives through to distribution interconnections, but there are some very important things about distribution interconnections. So then what I'm really talking about here are interconnections to the grid that's normally at voltages 34.5 kV and below. So you might have an interconnection at 34.5 kV There's some 25 kV distribution systems, and certainly 13.8 and even lower. And so these are in theory outside the purview of FERC, and therefore they are differently regulated, and the regulations typically come out and are state by state and utility by utility, and so they're have some nuances. Some of these are nuances that may make the process more difficult. Others are things that provide opportunities for maybe a quicker interconnection. So generally again, the queues are available. So each state has, without a doubt, produced some laws and regulations, and normally those will say, hey, the queues must be published, but they may be hard to find. So there's no organized way of accessing the queues like there is for the transmission process. Transmission process, where there's an ISO, they normally publish the queues, and the links I gave above are good sources. If you're outside an ISO for some reason, then it's always in the OASIS, which is, a part of the requirements that were first propagated in 888 and 889. Typically, one of the limitations here is that sales will be to the interconnecting party. So whoever you're interconnecting to, that's essentially becomes your market. Again, it's a generalization. There may be other possibilities. It may be that you can interconnect to a party and then purchase transmission service. So there are other things that can be done. Each situation is different and needs to be taken at differently. The third bullet is that market sales. So if you want to participate in the PJM market, the Cal ISO market, whatever market is you want to participate in, there is almost always an ISO level process, which may be that they want you to run through the ISO interconnection process, or it may be that there's a special process, so on and so forth. The next bullet I want to talk about is California Rule 21. For better or worse, we all know that lots of things come out of California, and Rule 21 is one of those. Those are the state regulations for interconnecting to the grid. Again, there's always a tariff involved. In the case of California, they're called the WDAT, WDAT, wholesale distribution access tariffs, I think. Anyway, so they have a specific set of processes for interconnecting at the distribution level. The interconnection processes, because they're state regulated, and anything FERC does is sort of for reference or suggestion, the processes may vary, and they may be difficult. We've seen a little bit of that. If the connecting party is interested, this can be an expedited process. So this is just an observation that, if you're interconnecting and you have a project that's ready to go, and you go to MISO and say, holy crap, it's a year and a half before I can get a MISO interconnection agreement, maybe you can interconnect at the distribution level, particularly if your customer is identified at that level. And then, there may be special processes for solar inverter-based generation. Sometimes there are incentives, sometimes there are extra requirements, but again, it's always an organized way to go about finding these things. So I'll give, so Mike, I think maybe you were gonna do this slide.
Yeah, thanks, Steve. So along with what Steve just covered, the technical requirements on interconnections, the newer inverters have the ability to do grid forming, grid following. So the utility may be very specific in, the types of, the specifications that are required for, getting a solar inverter connected. Communication capability, if something needs to be changed, or, something needs to be, there could be an operating characteristic that they need to make a change. They need to be able to do that through bidirectional communication. So, and then voltage and frequency support. Now this is limited. It's, only for a short duration, but still requirements to provide some support to the grid. Other areas, utilities are going to have their specifics. They may even say you will use this type of relaying. If you're wanting to connect to our system, you need to use these specific relays that we approve. Same with metering. They'll have requirements that need to be adhered to. Telemetry, communication, and SCADA. Specific polling requirements. Depending on the size of the solar facility. The polling may be, for a smaller facility, it could be several minutes. You get to larger facilities, that polling is going to be, shorter, less than a minute, or maybe even, every 30 seconds. And then, of course, BPS connected installations are even going to be more rigorous as far as, the telemetry requirements. We have, in some instances, there may be microgrid functionality that needs to be addressed, and there's a current guide, not a standard, but a guide that is going to be ready for balloting through the IEEE Power System Relay and Control Committee. That's P 2030.12, which Commonwealth is involved in. And then we have some examples for state requirements. Steve's given an example here with.
So again, we could go through a lot of detail, but we want to kind of define the scope of what's out there and what to think about and what you need to get at if you're going to interconnect solar. So I had an opportunity to interact with a customer, and they were interested in Philadelphia, or in Pennsylvania. So I just cribbed this. I said, all right, if I'm looking at Philadelphia in general, I first found that, there is a state code in Philadelphia that sets out what needs to be done. And then each of the transmission providers, I've got most of them that are operate in Pennsylvania, have then published a interconnection guide, which has elements of all of the data that Mike just talked about in the previous slide. So again, this is another one of these slides. I'm not expecting anybody to sit and make notes or anything like that. You'll get it in the presentation. But I wanted to give this example, and then the other point that we want to make is to varying degrees, this sort of information, this sort of process happens in every jurisdiction. So the generality is good. Then the corollary to that is you need to have somebody check these details at some point in the integration process of your solar project. Design requirements. Guess I will I've got your solar farm, a picture over there. There are a lot of design requirements that are required to interconnect a solar project. Now, in the top bullet there is a weak grid. We measure grid strength typically by a technical measure, the short circuit ratio. So if your short circuit ratio gets below 5 or 3 or thereabouts, particularly grid following inverter based generation has a difficulty staying online. So weak grids demand particular design requirement types of things to get your solar interconnected. And this has been an area of Commonwealth interest for some time. For those of you who are interested, we've published paper originally at CGRI, and we presented it in a number of forums that talk about some of the weak grid issues that you encounter. But that's an important thing. If I'm a developer, and certainly if I'm a contractor, I want to know about that issue right up front. You know, one of the first questions I ask, you know, and I'm sure you'll get irritated looks and that sort of thing, but I want to know what the SCR is. And then that follows on, there are, you know, protection issues that need to be dealt with. You need to be sure that you're meeting the requirements that are found. There may be special configuration issues that you need, special relays that you want, particularly if you have a weak grid. You're going to have to concentrate on coordinating with the inverter controls to meet the requirements of PRC 24, PRC 27, PRC 19. Those are areas that are entirely in flux because, like I said, those standards that sort of say how this should be done are heavily oriented to synchronous machines, and what you need to do on protection is a little bit is in flux. And you'll see more of that in a practical way as we get toward the end of the presentation. Transformer configurations are very, very important. There are two transformers that you need to know the configuration for. One is the plant transformer that typically converts the output of your plant from your collector voltage, typically 34.5, to whatever the transmission voltage is. I've done a project, for instance, where the conversion was from 34.5 to 46 kV. So not big of a, you know, but still there was a transformer there that was in a very weak system, and there were concerns to the point of not being able to interconnect the project about weak contribution from the grid under the contingencies that lines were lost. That problem was resolved. Last I knew, the project is in operation. Transformer configuration leads to another key area for solar integration. You got to get those things grounded. You got to deal with the transients. You know, Commonwealth's basic point of view on this is, you know, you need to get that collector grounded, which is not to say that you cannot operate ungrounded. But our basic point of view is that you can get it grounded, and that is something that can be done. In a lot of cases, people will suggest you know, EMT type studies. We are happy to do them, but only under the condition that their scope is clearly defined and they're clearly needed. So if you've got a strong grid and you've got a system that is effectively grounded vis-a-vis IEEE 142, or there's also a 60 series standard that addresses it, then it's not clear to me that you get any information out of a transient study related to the grounding. And then last but not least, this we know is a huge area, is harmonic and subsynchronous resonance studies. These are typically EMTP studies. The subsynchronous resonance can be broken down into concerns with series compensated lines. So for example, in New Mexico, you have a bunch of series compensated lines that interconnect between basically the Albuquerque area and Navajo in Texas, from West Texas into the Central Texas, Dallas, and then down into Houston. There are series capacitors, and they're concerned about what happens with the subsynchronous resonance. There's also the idea of subsynchronous control interactions. So if you look at a control of a typical solar inverter, there are, settings for that inverter, 40 different settings. Some of them relate to protection. So for an example that comes to mind is the factor K, which is supposed to be set mutually by the transmission provider and the inverter manufacturer. We see that sort of detail missing, and again, the consequences of that will come up. So we have another opportunity to pause and ask you some questions. Have you encountered any of these problems in your work integrating your solar project? Which ones have you encountered? Have you encountered a weak grid? Have you encountered the need to do a subsynchronous resonance or a control interaction study requirement? In general, is a more general way of that is, have you been asked to do an EMT or a PSCAD study? Have you had a project redesigned for a grounding or other issue? Have you been stuck in the queue and can't move forward? And have you had any unexpected network impacts? So for example, your system impact study came back and there was a requirement for, a $50 million network upgrade. And then another that we're seeing quite a bit of is, have you been asked to improve your reactive power ability? I saw a study earlier this week where, they were doing a cluster study and there were maybe 15 or 20 generators in the cluster, and there were 4 of them that didn't meet the reactive power requirements. So anyway, those are our questions.
Maybe a choice on there, Steve, should have been none of the above.
Well, yeah, none of the above. Put that in chat, or if there's something else you've got, put that in the chat. Bill, how are we doing on the poll results?
Yeah, so let's close it up right now. Let me just wait one more moment here, and
well, we can go on to the next slide and let people respond. But
well, here we go. We've got solar projects integration issues have encountered. It looks like 40% say project redesign for grounding or other issue. 25% say weak grid. 20% say stuck in the queue, can't move forward. And 10% say inadequate reactive power requirements, and 5% say subsynchronous resonance or control interaction study requirement.
okay, so these are that's good feedback. I mean, these are what we're seeing, and it's great to have the feedback that you guys are seeing these same sorts of things. So that's good, and I'm hoping that maybe there'll be some questions. We can be specific in answering your questions later on. Next slide is to let you know that for somebody, if you're a developer and you sell a project, okay, maybe you can forget about this stuff. If you're a contractor and you turn it over for ownership, maybe you can forget it. But for somebody, the interconnection agreement has things that you have to do throughout the life of the project. And I just took these from a typical interconnection agreement. You have to continue to provide reactive power. You can't just test the thing and say, I'm done. So 827, you've got to continue to do that. There's actually a mod 25 is a capability testing that is required on a regular basis throughout the life of a project. You need to continue to provide primary frequency response. You need to submit maintenance schedules. You may get interrupted and curtailed if there's a grid problem. You have to stay connected during a disturbance, so that goes back to our PRC 24. You have a responsibility to maintain your protection systems. You need to maintain power quality. So, that harmonic study, you can say, all right, it's met, but there's a mutual agreement between the transmission owner and the generator to maintain that. You have to obey switching and tagging rules, and you have to cooperatively complete any disturbance analysis. So I'm going to move on now, Mike. This is your thing of what can happen in reality.
Yeah, so for our remaining time, I'm going to run through these kind of quick with the time that we have left. So these disturbances, you can read more about them on the NERC website. They're interesting reports to read about, some of the, how these incidents occurred, and then, the reasons why the solar facilities, were not able to stay online. Now, in these incidents that are listed here, they're mostly, or most all of them are transmission-related faults. You've got faults on, 500 kV transmission, other 220 kV transmission systems. And then you have a solar facility that's located hundreds of miles away that trips due to the normal clearing of faults on the system. So Blue Cut Fire, that was 1,200 megawatts. That happened back in 2016. That's a picture there from, the carnage of that fire, just east of Los Angeles. Yeah, the Canyon 2 fire, 900 megawatts. Palmdale Roost, and Angeles and Palmdale Roost, they're similar events. I've got the dates mixed. Angeles Forest was actually April 20th. But the amount of PV generation lost is, about 1,500 megawatts for Palmdale and 1,800 for Angeles, and then 1,000 megawatts lost in San Fernando. Various reasons why the inverters were not able to ride through these system disturbances. Sub-cycle transient overvoltages. Their inverters were not set correctly, to ride through these incidents. AC overcurrent. There were a number of, like DC reverse current in the inverter. One key type of a commonality, I guess, between these different ones, momentary cessation. And so that's kind of a common denominator in a lot of these, that the inverter output just stopped, and that a control function that was improperly set at the beginning, just a default of the manufacturer, that when they see a hiccup on the system, that the inverter output is just going to just shut off. And so then the problem is there's a certain amount of time to ramp up and get back to where they were. So, momentary cessation is kind of like a big buzzword coming out of NERC. Next slide, we move to an incident that was in Texas, the Odessa disturbance, and that one, we had over 1,100 megawatts of of solar that was lost during this disturbance. And this was a failed arrestor at a combined cycle plant. And so then you can see how widespread. You see the red circle in that graphic, that's where the fall was. And then the orange circles, that's actually wind. But then, I mean, Texas is a big state, and you can see how widespread, you know, that fault caused solar inverters to trip offline. And with all these faults, they were cleared in normal time, you know, within a few cycles, but yet it caused, you know, the solar facilities to drop off. So reasons for you know, the loss of you know, of the inverter, we have, you know, phase lock loop, loss of synchronism, inverter AC overvoltage and or feeder AC overvoltage. Already discussed the momentary cessation. That's another. It's still, despite all the previous incidents that came out of California, you still had momentary cessation that was occurring in Texas. And then also inverter under frequency and or feeder under frequency.
So Mike, I think one of the things that we are saying is, all right, this problem isn't limited to California, that we expect to see these sorts of problems occur in other places as the penetration of different inverter-based resources, including PV, gets, you know, becomes more widespread.
Exactly. And expect NERC to be coming out with reliability standards. So if we go to the next slide here, you know, the NERC key findings and recommendations. Okay, first bullet point is they feel the industry is not sufficiently implementing their recommendations. So they want people to pay attention to their guidelines. Okay, the second bullet point, FERC generator interconnection agreements. In a lot of cases, they need to be updated and they need to be improved. The third bullet point, and this is a series of improvements to NERC reliability standards to address, and these are systemic issues that continue to happen despite, you know, the previous incidents. There's still these, you know, they're still having problems. So, you know, NERC is good with, okay, we have you know, like PRC 24, that you document that you have this coordination, you work through this and you document it. Well, that's fine that you document it, but there needs to be performance-based requirements. So that's probably going to be something that you'll see coming out of NERC, is that, okay, you have to prove it. And so along with that, the performance assessment and mitigation. Okay, if you have an incident, then prove that you've corrected it and that you know, you've taken a proactive correction. There's most likely going to be a change with the ride-through standard in lieu of PRC 24. Analysis and reporting to NERC. There's a lot of stuff that, you know, happens that doesn't get reported to NERC. So expect more, you know, coming from that. And then lastly, you know, NERC is recommending that a lot of stuff can be prevented with proper modeling and studies. And so your PSCAD modeling, EMTP studies, they feel that, you know, we could prevent a lot of incidents with the proper, you know, before these facilities are brought online. You know, you've addressed issues.
So let me just offer an anecdotal. In a project that will go unnamed and an ISO that will go unnamed, we were trying to get some information from the ISO as to, you know, all right, so what is the requirement for the voltage control and ride through and the other stuff. And they said basically, well, just submit whatever data you have from your commissioning and that'll be good enough. So again, this is an evolving area, but it may catch you up. At this point, we've probably gone beyond our planned time a little bit, but we're here to answer questions for as long as we can, and as long as you guys have interest and time. Del, maybe you have some questions in chat.
At this time, Steve, we haven't received any questions in yet. I will look a little bit further, but while we wait for some questions to come in, one thing I wanted to let everybody know is that our next webinar is coming up February 23rd at the same time, and the next webinar will be about inverter studies. So there should be a link coming out soon. We will have our colleagues send it out in email again, and also on LinkedIn and on Commonwealth's Facebook. So look out for that in the future, and we hope that all of you join us again next time. So I will continue looking for questions.
We've got a quiet group today. That either means our presentation was so boring, nobody has any questions, or so good, we answered them all.
All right, just a minute, Steve. It's not that quick. I've got one coming in for you here. Hold on. For some reason, I can't see them, so I'm having IT help here with me, but I have a couple questions for you. So the first one is, do you see requests or requirements for lighting studies for PV? The assumption that some regions this is unnecessary, while others it's likely to occur.
So I think the word that you were trying to get there was lightning studies.
Yes, yes.
Yep. And the answer to that would be, based on our experience, that would be a very likely outcome. So, and again, this actually ties to an old experience where Commonwealth has done this for years and years, is when you do transmission line design, the first thing you go is look at a map of lightning activity. So for example, if you're involved in California, they don't get much lightning. And you can see that if you're sort of educated or know too much. There frequently aren't ground wires on even transmission lines in California. In other places, that would be a disaster. So a lightning study would be of interest. Now, again, all of that really shouldn't require a terrifically huge study, and it ties into the grounding issue, right? So one of the things that we do with grounding is do a lightning impact study. But normally, if you can show that your plant is effectively grounded, that might take care of it without doing a in-depth study. But yes, that's certainly going to be an issue in some places. So for example, in Florida, I would think it would be a big deal. As I said, in California and in some other places, incidents of lightning.
All right, we got a few more questions that have came in. Can you elaborate on why the low side of the solar transformer should be grounded, and should delta be avoided?
All right, so let's talk about that in as organized a way as we can. So we first need always to be clear as to what transformer we're talking about. So the first transformer I'm going to talk about is the low voltage transformer that transforms between a low voltage, typically something in the range of 480 volts to 690 volts. I've seen one recently, Premac Power Electronics is putting out a inverter that can go up to 1500 volts on the low voltage side. And then that transformer ties to your collector system, at 34.5 kV or some other voltage. Because of the inverter requirements, the low voltage side of that transformer must be ungrounded. So it'll either be a delta or a ungrounded Y. And that may vary by manufacturer. Tesla does some stuff, and you know, you'd want to be very careful about what their requirements are. The high side of that collector transformer, there's a lot of misunderstanding out there that should be ungrounded. It does not have to be. So the main requirement is the inverter people don't want zero sequence flowing through that that transformer. They don't want a zero sequence contribution. Then you have your collector system. The collector system typically ends up in a bus, and then there is a transformer that connects from medium voltage to whatever your transmission voltage is. The requirements there vary from utility to utility for different reasons. Frequently, the utility may say that they don't want any ground contribution from the project, which means that you've got to put a delta in that in the 34.5, the medium voltage side of that transformer. But that's not uniform. So those particular requirements really depend on the particular transmission entity that you're interconnecting to. They may be different depending on whether you have a weak or a strong grid. So the design of that transformer is an important element. Frequently, when you have a delta, then in the collector system, to block the zero sequence current, then that says, all right, to remain effectively grounding, maybe we need a grounding transformer in the collector system.
All right, we are really out of time, but I'm going to try to see if you can get to I have two more questions for you really quick, but before we do that, I want everybody to know that the handout is available in the for download. The PowerPoint is available in the handout section on the control panel of the WebEx, so you can go there and grab that. And Steve, I don't know if this is going to shut us off, so you might have to speak really fast, but
so let's make sure they know that they can email us with questions.
Yes, and we will, and we can try to respond out to the questions that we don't get to when we can email out to the attendees. But one of them is, if we don't get to these, have you seen any integration of synchronous machines to provide fault current due to the inverter-based generation? And there was one more after that. Is there any movement to creating a standard for the requirements across all ISOs, a uniform process across the country?
Okay, so let me answer those questions as quickly as I can. The answer is yes. We've seen certain application of synchronous generators. I think technically the story is still out on whether those are important or not. So we participated in a project in New England where they explicitly added a synchronous generator, and the reason for that is they wanted to make sure they had the fault currents and the inertia there. Then of course the other example of that is there have been synchronous generators added in West Texas. I suspect a study of it would show that there's a lot of conversation. Whether that's valuable or not, I think is still a open question. It solves one immediately thing. It increases the effectiveness of the grid. The second question, my old mind is sort of lost.
Hey, one quick point, Steve. That's synchronous condensers, right?
Right.
Yeah.
Okay, so right before you do that, I'm gonna let you, one of the questions that I've been working on the backside to answer was, could we put the link in for the February 23rd presentation into the chat so people could go ahead and register for that? So that has just happened. So any of you that are still online, if you'd like to click that link, you'll be able to register right now for next month's presentation and webinar to earn additional PDHs. And for you, Steve, the last question was if you think there's any movement to create a standard for the requirements across all ISOs.
So the answer is sort of, kind of. So one of the big deals with the implementation of the FERC orders is to maintain regionalism and regional requirements. But at the same time, NERC is an overall body and is putting across the board requirements. I think it'll be a very long process before there's sort of national requirements, if it ever comes. So for example, in New England, the ISO is pushing for so-called generic models for all of these things, whereas in Texas, they're insisting on user-defined models. So there is a lot of regional variation. I think you can expect that regional variation to continue for a long time. You know, there is a push for federalization and that sort of thing. And there are, like I said, there are some basics that have been established since the 90s. But to see anything that would get into the details of, say, your plant transformer should look like this, I think that's a long time coming. And I know that's an important issue because, you know, your supply chain is important. So you might like to order a whole bunch of transformers to be used in a variety of jurisdictions. But, you know, if the requirement in jurisdiction X is Y and the requirement in jurisdiction Z is W, then, you know, you've got a problem.
All right. Well, I want to thank Steve, you and Mike for sharing with all of us today, and let everybody know that when you receive your post-webinar email, there will be a link in that for a recording back to today's session if you'd like to go back to any of it and review any of what Steve and Mike have shared with us. So thank you all for joining, and we hope to see you next month.
Thanks for listening.
Yeah, thank you.